Video I'm going to be working AP Pre-Cal Homework 2.2, and this is going to be mostly about the end behavior about polynomials. And so we're going to look at f of x first, which is x to the 3 minus 2x to the 6. Okay, so I think really what we're supposed to be looking at mainly here is the 2x to the 6. It's the highest degree term. That's going to tell us basically everything we need to know about the overall behavior of the polynomial. So we're going to go back and we're going to say, all right, the sign of the leading term, well, I'm going to be more specific. I'm going to say the leading term is negative 2. And then the degree is 6. So when they ask, well, the sign of the term is negative and the degree is even. Okay? Then we'll complete the statements because it's a negative degree an even degree polynomial with a negative leading coefficient, it's going to look like y equals negative x squared, at least on the outsides. And so as x approaches positive infinity, f of x is approaching negative infinity. Okay, that's the arrow on the right here. And then as x approaches negative infinity, that's the other situation we have to consider in this class. As x approaches negative infinity, f of x is approaching negative infinity again, so I have to say negative infinity. The second one says, using limit notation, describe the end behavior of the polynomial negative 4x to the 5 plus 2x minus 1. So we're going to do the exact same thing we did up above. We're going to figure out what's the high degree term. It's the x to the 5, that's the biggest exponent I see. So let's say, all right, the degree is 5. And then the leading coefficient, that's going to be negative 4. Okay, so if it's an odd degree polynomial with a negative leading coefficient, it's going to look overall like the graph of y equals negative x cubed, or negative x if you prefer to think about it like that. Okay, y equals negative x cubed looks kind of like that. And so I'm going to use that in behavior, and I'm going to say, all right, I'm saying the limit as x approaches positive infinity of p of x, and you could say of negative 4x to the 5 plus 2x minus 1, that'd be a lot of extra writing, you know. Okay, as we approach positive infinity, p is approaching negative infinity. And the y coordinate is going down, it's getting less and less without limit. So the limit as x approaches negative infinity of p of x, well, as x approaches negative infinity, y is approaching positive infinity, so we'll say that is positive infinity. Oops, that's what's going on the screen there. All right. Number 3 is going to ask us pretty much the same thing, but with slightly new wording. So using limit notation, describe the end behavior of g as the input values increase without bound. That's going to need a translation. All right, so when they say input values, okay, we know that means x, generally. Unless x is the output, which we have already seen happen in this class once on homework. But in this case, it's g of x, so x is the input. And as x increases without bound means like it never stops. So if it continues to increase forever, what that means is x is approaching positive infinity. Okay, and then you see the next one is going to say decrease without bound. That's going to mean x is going to approach negative infinity. We'll get there in a second. So g, we're looking at g is a 4th degree polynomial with a positive leading coefficient. Okay, so degree is 4, leading coefficient is positive 3. Okay, so an even degree polynomial with a positive leading coefficient, that's going to look like y equals x squared on the outsides. And so as x increases without bound, we're thinking of this end behavior. And I'm going to say that the limit as x approaches positive infinity of g of x is equal to positive infinity. Okay, because of the behavior on the right side of the graph. Okay, and we've seen this language in AP Classroom on multiple choice items, so we definitely want you to be aware of this. And then the next one is using limit notation, describe the end behavior of h as the input values decrease without bound. So that's going to mean x approaches negative infinity. h is going to be a 5th degree polynomial with leading coefficient 1. So degree 5, leading coefficient is 1, positive 1. And so if it's a positive coefficient on an odd degree polynomial, that's going to look like y equals x cubed. So if we're saying decrease without bound, we're approaching negative infinity. We're thinking here y is going towards negative infinity. So we'll say the limit of h of x as x approaches negative infinity is equal to negative infinity. All right, now we're looking at a graph and going to describe the end behavior of f using limit notation. Now I do think we are assuming that this graph, let's put some arrows here. Okay. And all right, well, we can describe this end behavior. We'll say this is the graph of f, so that the limit of f of x as x approaches positive infinity, okay, as I go farther to the right, okay, I'm going up. That's going to be positive infinity. And then as x approaches negative infinity, I'm going to continue to go down. So I'll say that the limit of f of x as x approaches negative infinity is negative infinity. Now this one is going to give us a picture of a graph, and this is the picture of a polynomial function p. Write an equation that could represent p. All right, now we're going to say could because we can't really see the scale in y. We don't see that there's no y-axis, and it's not labeled that those grids are 1. They're definitely not. I remember when we made this graph, it was definitely much larger than 1. Okay, but what we're going to say is, all right, p of x, it's going to be some leading coefficient a that we're not going to be able to find. And then I'm just going to kind of look at the zeros and their multiplicities. I've got x equals 0 having an even multiplicity because of the bounds. Okay, that's going to be, let me think about it. Oh yeah, what I'm wanting to say is the easiest thing for us to do is say it's a double root. Keep the degree as low as possible. And then at x equals 3, okay, I'm seeing hesitation, so that means it's but it is also changing signs. So if it's changing signs hesitantly, that means it's like a triple root or a quintuple root or some odd multiplicity root that's greater than 1. But I'm just going to say it's a triple root. So p is going to be some number times x minus 0 squared times x minus 3 to the third, because each of these factors is coming from the zeros in the same way that the zeros come from the factors when we're solving an equation. All right, now but there's a little more we can do here, right? Because we can look and we can kind of see the end behavior of this polynomial. Oh, that's interesting. Didn't expect that. Okay, I didn't do it for that one. So looking at the end behavior, we can see that, okay, this is an odd degree polynomial because the arms are pointing in opposite directions, and it's going to have a negative leading coefficient because as x approaches positive infinity, y is approaching negative infinity. And we see that in our formula that we're going to have 5 total powers of x if we were to multiply this out, which we're definitely not going to need to. But since I'm saying this one's degree 5 with a leading coefficient that must be negative, okay, a really has to be less than 0. So I'm going to say one possible equation that could represent p would be p of x equals, I don't know, negative x squared times x minus 3 cubed. Okay? But it could be negative 5 if you wanted. It really doesn't matter. Right. Now the next one says that must represent f. But looking at this now that I think about it, I feel like it's still kind of, not certain because of the multiplicity of the root at 1. Now, will admit I'm not like the most studied on what a quadruple root looks like, a root with multiplicity 4. If it looks more like y equals x to the fourth does at the origin, where it's a little flatter near the 0, I'm not certain. I'm just going to assume this is a double root, and we'll write an equation of minimal degree that could represent f. And we'll just do that. So rather than must, we'll just keep the degree to a minimum. So we'll say first, kind of label our zeros, x equals -2, and that's going to be a single root because the graph is passing through the x-axis confidently. And so I'm going to say f of x, and we're looking for an equation, so we need something with an equal sign. F of x equals some number times x minus -2. So x minus -2 would become x plus 2. That's going to be to the first power because it's a single root. And then my other root is x equals 1, and that looks like a double root to me. It's bouncing, and I guess it could potentially be a quadruple root. I'm not sure we have enough information to say that for sure, but to keep it to a minimal degree, we could say it was x minus 1 squared. Okay, then we'll use the extra piece of information we were given right here. So 0, -6. So I'm going to say f of 0 equals -6. Right? So using that, that would be -6 equaling a times 0 plus 2, because we're plugging in 0 for x and -6 for f, and 0 minus 1 squared. Okay, so -6 equals 2a times -1 squared would be +1. And that means that a equals -3, but a isn't really what we were looking for. We were looking for an equation for f. And then f of x equals -3 times x plus 2 times x minus 1 squared. And in this class, we are not going to need to distribute that out by hand. All right, now the next one's got q of x. And kind of the same idea, write an equation that could represent q. So I'm just going to assume this is a double root, so x equals -3 multiplicity 2. And so that would give me an x minus -3 squared. Then I've got x equals -2. I'm going to assume, oh no, I'm not going to assume, I know that's a single root because the graph is passing through confidently. So that's going to be multiplicity 1. So x minus -2 to the first power. And over here at x equals 2, we've got a bounce. Assume that's a double root. X equaling 2, double root. I've been writing the multiplicity, so I'll say multiplicity 2. And then x equals 3, multiplicity 1. Graph is passing through confidently. So I had x equals 2 squared, and then x minus 3 to the first power. So yeah, barely not on. Okay, now it's got to be an equation, so I'm going to need q equals. But then there's also the possibility of a leading coefficient, and I need to be considering the in behavior here. Okay, so if I put some arrows over here, it would sure look like, again with the triangle, it would look like it's going to be an even degree polynomial with a negative leading coefficient. And if I added up all the exponents, 2, 3, 4, 5, 6, okay, I'm seeing an even degree. Okay, I need to have a negative leading coefficient. So I'm going to say a needs to be less than 0, so I'm just going to make it -1. But you could do something else. So q of x equals -1 times x plus 3 squared times x plus 2 times x minus 2 squared times x minus 3. Okay, now this next one, okay, an equation that must represent g, assuming that x equals 2 is a double root. Okay, so we'll write a minimal degree polynomial that would possibly represent g. So x equals 2, double root, and x equals -2, single root. Graph is passing through confidently. Okay, and a y-intercept at 0, 1. I'll come back on that in a minute. So g is going to be equal to some number times x minus 2 squared, because x equals 2 is the double root, times x minus negative 2 to the first power, because x equals negative 2 is a single root. And then we're going to use the data we were given. 0, 1 is on the graph, so that means that g of 0 equals 1. So 1 equals some number a times 0 minus 2 squared times 0 plus 2. That's where 1 equals a times positive 4 times 2. So 1 equals 8 times a, so a is 1/8. My equation for g is going to be g of x equals 1/8 of x minus 2 squared times x plus 2. Okay. And if we do this thing where we solve for the leading coefficient using a point that we were given on the curve, we don't even have to worry about the end behavior, because that's just taken care of by the solving aspect. You know, if it was going to end up having a negative leading coefficient, we would have solved for it that way, and it would have shown up in the algebra. Okay, number 10, back to could. All right. Okay, x equals 0. This looks like a triple root to me. The graph is hesitating as it goes through, so I'm going to say multiplicity 3. And then x equals 2. That's going to be multiplicity 1 for sure, because the graph is passing through with confidence. So I'm going to say, well, h of x is going to equal some constant a times x minus 0 to the third power times x minus 2 to the first power. And considering the end behavior, it's like an even degree polynomial with positive leading coefficient, because both of the arms are pointing up. So it's kind of like y equals x squared. Okay, I'm seeing 3 plus 1 is 4 total powers of x, so this is, you know, believable. But from this, we know that a needs to be positive. So I'm going to say, you know, I'll let, this time I've been letting a equal 1 or negative 1. Maybe I'll let it equal 10. Really be anything you wanted, just as long as it was greater than 0. Now here we've got another polynomial graph, and I'm going to just kind of color in some arrows down here. Okay, based on the graph, is the degree of h even or odd? Okay, I'm going to say it's odd because the arms, the end behaviors, are pointing in opposite directions. Based on the end behavior, really, the opposite end behaviors. Is the leading coefficient positive or negative? Okay, that's what I'm going to say, is that one went up and one went down for my reason. Is the leading coefficient positive or negative? I'm going to say positive. Reason is going to be because, well, as x approaches positive infinity, y approaches positive infinity. That will be true in general. That whatever the limit of the polynomial is as x approaches positive infinity will be the same as the sign of the leading coefficient, if that makes sense. That didn't, you can come talk to me about it if you're interested. But we can really determine the leading coefficient based on the right-hand behavior of the polynomial. So positive, and that's going to be because the limit as x approaches positive infinity of, we're calling it h of x, is positive infinity. Okay, and then writing a factored form equation that could represent h, that's what we've been doing the whole time. H of x is, okay, odd degree positive leading coefficient. I'll just assume the leading coefficient's 1 this time. Okay, this is x equals 0, looking like a double root. And then this is x equals 3, definitely a single root. Okay, so h of x equals x minus 0 squared multiplied by x minus 3. All right, now we're going to take it back a little bit. We're going to ask you to think about something we were talking about a week or two ago. If h has a point of inflection at x equals 1, which is definitely believable that it does, I'll label that right there in blue, when is h both decreasing and concave up? Right, so h decreasing, just to remind you, on the graph, it's as we move left to right, we're going downhill. And h concave up means that if we're looking at a picture of the graph of h, the graph is smiling. Okay, so if we're decreasing while smiling, we're looking for a graph that kind of looks like that. Okay, and I see some. It's after 1, and it's before it hits the minimum. Okay, so it looks like it's at 2. Now, after 2, it's not, h is not going to be decreasing anymore, so it can't be both decreasing and concave up. It does continue to be concave up because it continues smiling what looks like forever. So let's say this is my interval of decreasing and concave up, decreasing at an increasing rate. We'll say that's x between 1 and 2. And we're not going to let you just forget about that. Right, we're going to need to continue to practice that so that we can become more fluent with it and it becomes easier and we'll be really confident with this stuff by the time May hits. All right, now we're going to sketch some polynomials, just a couple of them before we're done. And I think this is good practice. You know, we did some of this last time, we just didn't ever have any triple roots. So I would expect both of these to have a triple root. Yeah, there we go. 2 of them that are having a triple root. Now the thing about a triple root is that because of the limitations to the types of factoring that we do in this class, the only way you'll be given a triple root is by something that's already factored, or that you can factor an x to the 3 out of like this. Those are really the only 2 ways it can happen. So it's going to be pretty limited. What are we thinking here? A sign chart. Pardon me, I had to think, because we've been doing really similar work in my calculus class, and I was just trying to remember the approach I'd been taking in pre-cal. All right, so I'm going to start off with a number line, and I'm going to identify my zeros. X to the third, that gives me x equals 0 as a root. Okay. And the third power means it's going to be a triple root, and I'm going to write that in, because that's going to change how I sketch the graph. The graph's going to be hesitant. Then over here, x minus 4, okay, that's going to give me a root at x equals 4. Now that one's going to be a single root, but I'm not going to write anything. It's just going to pass through normally like we would expect. Okay, now I also am noticing that negative out front, but I'm still going to use a test point myself. I mean, if you want to try to start with the end behavior, that's, you know, that may have been what I recommended you to do last year. Maybe what I recommended to you next year. But this year, I am suggesting we use a test point. So test point for me, I'm going to choose something from the far right edge. Okay, something greater than 4. Maybe x equals 5. Okay, when x equals 5, y is equal to negative multiplied by 5 to the third, which is going to be a positive number, multiplied by 5 minus 4, which is also a positive number. So negative times 2 positives is negative. And then over here at a single root, the sign will change because the multiplicity is odd. And then at a triple root, the sign is also going to change because the multiplicity is odd. It's just that the graph is going to hesitate. Okay. Now, if we look at this, you know, in terms of what we were talking about today, we would say, okay, well, y equals, if we were to distribute this, negative x to the fourth plus 4x to the 3, that would be a 4th degree polynomial with a negative leading coefficient. So that means that on both sides, we'd be going downhill because it would look like y equals negative x squared on the outsides. Okay, but that's what we're seeing. It's going negative, and we kind of even said last time that, you know, whatever it's doing on the outside, it's going to do going towards infinity. Okay, so I think that's enough justification for why I'm going to be starting from below and be coming up. Now at a triple root, the graph is hesitant. It's got to have a point of inflection, so I kind of approach aggressively and then really slow down. And then we're going to pass through. I actually think I could do a little better. I'm going to give it a second shot. There we go. And then we go up, and we're going to have to come back down and pass through at x equals 4 with some confidence, okay, because it's a single root. I'm going to angle it down like that, and there we go. We've got ourselves a sketch. Right? If we want to, we can come in with a y-axis, and that would make our sketch look extra nice, and that happens at x equals 0. And then we can just go like that, and there we go. We've got ourselves a really nice sketch of polynomial y equals negative x cubed times x minus 4. All right, now the last one, x times x plus 2 squared times x minus 3 to the third. I'm going to, again, start by making a number line. That might be a little bit high up. I might move that down a little bit. Okay, and make sure it's also on screen. And I'm going to label the axis with my roots. So I've got x equaling 0, x equaling negative 2, and x equaling positive 3. And I'm just going to draw this, not necessarily to scale, where I would feel comfortable putting these things for my sketch. Okay, and then I'm going to think about the multiplicities. At x equals 0, I have a single root because it's just x to the first power. X equals negative 2 is going to be a double root. I write multiplicity 2. X equals 3 is going to be a triple root, which is multiplicity 3. Okay. Now this single root, that's multiplicity 1, and that'll be mattering when I go to determine do I have a sign change or not. That's what I'm going to do right now. Get a test point. Let's see. Start here. Choose x equals maybe 1 this time. It really doesn't matter. Just can't choose 0, negative 2, or positive 3. Okay, when x equals 1, y is going to equal 1, which is a positive number, times 1 plus 2 squared, that's going to be a positive number as well, times 1 minus 3 is negative 2 to the third power. If I take a negative number to the third power, I'll have negative. Okay, so 2 positives and 1 negative, that's going to be negative. So I'm going to put negative right there. Okay, right here at x equals 3, that's multiplicity 3. That's an odd multiplicity, so I'm going to have a sign change. Now, the fact that it's multiplicity 3, it's a triple root. The graph's going to be hesitant as it goes through there, but we'll be able to deal with that. Okay, x equals 0, that's a single root, so I'll have another sign change here. But then over here at x equals negative 2, that's a double root. Multiplicity 2, even multiplicity, no sign change. Yeah, so I've got my sign chart made. I'm ready to sketch my graph. Okay, it might be good right now to stop and double check and make sure you've done it right, and a good way to check would be the end behavior of this function. If we look over here at the degree, I'm going to have 1 from the x, I'm going to have 2 powers of x from the x plus 2 squared, so it's a total of 3 now, and then the x minus 3 cubed, that has 3 powers of x, and that's going to be a total of 6 powers of x. That's an even degree. The leading coefficient is going to be positive because there's no negative x's anywhere. And so an even degree polynomial with a positive leading coefficient, it looks like y equals positive x squared, so it's positive on the outsides, and this is making sense. Okay, so I'm going to need to probably get rid of my test point calculation. Hate to do it, but got to get a sketch here. So I'm going to come over from about here, and the graph is going to bounce, so I'm going to prepare it for that by kind of approaching and then softening up, coming up. And then, okay, I'm going to go from positive to negative, so I'm going to have to turn back around. And that's what we're saying. Between every 2 zeros of a non-constant polynomial, there must be a relative maximum or a relative minimum. And it's because the continuity and smoothness of the polynomials. Okay, so there we go. And there we've got ourselves a nice sketch. I'm going to come in and draw a y-axis. But I don't think you need to if you don't necessarily feel like it. And that was exactly lined up, but it'll do. I'll label my axes, I'll say that's x, this is y, and then there we have a really nice sketch. Alright, yeah, that's going to be all for this video. That's the last problem, so thanks for watching.